I'm going to walk you through how to create a slope field, maybe what it's used for. If you don't know how to solve differential equations or what that means, well, that's super important background knowledge. So watch another video, mine or somebody else's, before you watch this video on slope fields. So you should be able to, given a differential equation, sketch a slope field. And those slope fields are used to visualize the solution curve of that differential equation. And the nice part is slope fields can be used for non-separable differential equations. Basically, differential equations you can't solve by hand. I'll link to this Desmos exploration in the notes that might give you a little bit better handle on what slope fields look like. Okay, the reason solving is in quotation marks is, well, we can solve dy over dx equals x the normal way, but I want you to see how that's related to the slope field. So College Board, if you have to do a slope field on free response, they'll give you an interval, and this is way too wide, but that's okay. So -3 to 3 by -3 to 3 is actually 49 different places. And, well, let's take a step back. What would it mean to solve this differential equation? That would mean I find the y equals some function of x that has dy over dx equals x as its derivative. So we don't really know what this function is. Does that function go through the point 0, 0? We don't know. Does that point does that solution equation go through 1, 0? We don't know. Does that solution go through 2, 3? We don't know. However, we could still find the slope of that solution equation if it did go through these points. What do I mean by that? So, well, dy dx evaluated at 0, 0 would just be a slope of 0. Let's get rid of some of these. Dy dx evaluated at the point, what did I have, 1, 0? That would be a slope of, well, we just used this equation. That tells us slope. Well, that'd be a slope of 1. Dy dx evaluated at 2, 3. We don't know if that's the right point for the solution curve to go through, but if it did, that would be a slope of 2. The slope field is just a visualization of that idea. Okay. I have some room to work off to the side, so let's draw some axes first. See if I can get something straight. That's not bad. Okay, and remember, we're trying to visualize dy over dx is equal to x. Okay, so let's think about what's going on at 0, 0. That would be a slope of 0, so we draw a slopette, a little line segment with a slope of 0 at the point 0, 0. Let's try the point 1, 0. What would the slope of the solution curve be if it went through 1, 0? Well, we use our dy over dx equals x, so we just use the x value. We get a slope of 1. And you don't have to get that slope exactly perfect. It just has to be about right. What I mean by that is this could not be a slope of 1. That's too low. If you got a ruler, maybe my slope here at 1, 0 isn't exactly 1, but it's at least close. All right, let's think about this. If the solution curve went through the point 2, 0, what slope would that solution curve have at 2, 0? It would have a slope of 2. So I'm going to try to get a slope of 2. What I'm doing is I'm trying to aim right here, connecting a point, 1 to the right and 2 up, with that little slopette I'm trying to draw. Okay, at 3, 0, the solution curve would have a slope of, oh no, 3. And so maybe that's not exactly correct, but what I mean that the College Board doesn't care if you get exactly the right slope. The slope at 1, the slope at 2, the slope of 3, those should look increasing. Okay, so this is going to take a while. Remember, we're trying to draw a slope field from x equals -3 to x equals +3, y equals -3 to y equals +3. So can you figure out a pattern? Well, let's think about this. What's the slope at 0, 1? Well, the slope is determined by the x value. So that would be a slope of 0. What would the slope of the solution curve be at 0, 2? That would also be 0. Oh, in fact, whenever the x value is 0, the solution curve would have a slope of 0. Let's see, 1, 1 has a slope of 1 if the solution curve went through 1, 1. 2, 1 would have, slope of 1. Oh no, slope of 2. 2 1's over here. Come on, Shoal. 1, 2 would have a slope of the x value 1. Oh, now I'm getting it. Whenever the x value is 1, the slope of the solution curve would be 1. Whenever the x value is 2, the slope of the solution curve would be 2. Whenever the x value is 3, the slope of the solution curve would be 3. Oh, we need to keep drawing. Okay, so -1, 0. Right here, what would the slope of the solution curve be if it went through -1, 0? -1, just the x value. In fact, all these points that have an x value of -1 mean the solution curve would have a slope of -1 if it went through those points. Slope of that's too steep. -2, -2, -2, -2, -2, -2, -2, -2. -3, -3, -3, -3, -3, -3, -3. Okay. So that red part is what the slope field would look like. Let's change the color here. Okay. So I want to get rid of this stuff. Remember the solution. Let's see. First we'll have to separate variables. dy is equal to x dx. Integrate both sides. Oh, I said dx. The antiderivative of 1 with respect to y is y plus a constant. We'll take care of that on the right. The antiderivative of x is x squared over 2. So this is a general solution curve. And hopefully you can see, if I drew anywhere and tried to follow get a similar slope whenever I go through points, I'm going to get what looks like a parabola, 1/2 x squared plus some number. If I start down here, I'll move to the right, and notice I don't have to go through those points, but, so like here, what I'm drawing is pretty much parallel to these slope points around. So then I trace to the left, try to follow the slope field. They're like directional arrows. Hey, where to go? So these green things, let me get rid of that one. These green things are what the solution curves look like. This is a nice example. Pretty easy to do. And we can solve dy over dx equals x by hand, so we can confirm what we're looking at. Okay, so this is a much more appropriate differential equation to use the slope field for. We can't solve dy over dx equals x plus y by hand because we can't, well, I can get x dx plus y, I know that doesn't look like a y, plus y dx, but I can't get the y's with the dy's only, so I can't separate this thing. However, we can see what a solution curve might look like. So dy over dx is x plus y from -2 to 2, -2 to 2. Get some axes here. Yellow might be too light. Let's do green. So the slope of the solution curve is determined by adding the x-coordinate and the y-coordinate together. Let's start off with some easy ones. So does the solution curve go through 0, 0? We don't know, but if it did, it would have a slope of x equals 0 plus y equals 0 is 0. So at 0, 0, I draw a horizontal slopette mini tangent line. Not sure what to call that. Let's think about 1, 0. If the solution curve went through 1, 0, it'd have a slope of 1 plus 0 or 1. That's not quite steep enough. How about, there we go. Does the solution curve go through 2, 0? We don't know. If it did, the solution curve would have a slope of 2. We better try some harder ones. Maybe we should change the color as we go so it'll be easier to see. So let's see, 0, 1. That's right here. Okay, what would the solution curve have as a slope at 0, 1? 0 plus 1 is 1. At 1, 1, the solution curve would have a slope of 2, 1 plus 1. Our equation, dy dx, is equal to x plus y, says add the y and the x to get the slope of the solution curve. Let's see, what about 2, 1? What would the slope of the solution curve there be? That would be a slope of, 3. All right. Let's do some more. Oh, having fun with colors. How exciting. Okay. So let's do 0, 2. That would give us a slope of 0 plus 2, or 2. 1, 2 would give a slope of 1 plus 2 is 3. It's pretty steep, or at least steeper than the slope at 0, 2. And a slope at 2, 2 would be a slope of 4. Ooh, even steeper. All right. Let's finish this off. Well, maybe we should draw in some of these negatives. Do you see the pattern that these three are supposed to have the same slope? 0, 2, 1, 1, and 2, 0. Why is that? Because we're increasing the x value by 1 and decreasing the y value by 1, which means we get the same sum. So that could save some effort, but I'm not going to quite do that yet. Okay, let's do some more of these. So how about let's start all the way here at negative 2, positive 2. That would give us a slope of, or the slope field has a slope of 0. Negative 1, 2 is going to be a slope of 1. Negative 2, 1 also has a slope of 1. Isn't that right? Oh, no, that is not correct. That didn't sound right. Negative 2, 1 has a slope of negative 1. If you got that before me, good job. Negative 1, 1 has a slope of 0. Negative 1, 0 has a slope of negative 1. What else is going to have a slope of negative 1? 0, negative 1, and 1, negative 2. Can you find any other places that are going to have a slope of 0? 1, negative 1, 2, negative 2. What's this slope here? Well, hopefully you can see these diagonals forming. That's a slope of 1 if we're following, but let's see, is that right? 2, negative 1, 2 plus negative 1 is a slope of 1. Oh, this is how you speed things up. So 0, negative 2 has a slope of negative 2, negative 2, negative 2. And then negative 1, negative 2 has a slope of negative 3, negative 3. And then I know this is going to be negative 4 at negative 2, negative 2. Okay. So remember, we couldn't solve the differential equation x plus y. dy dx is x plus y. But we can visualize that solution. Let's try to do that now. So let's say we were given the point 1, 1. The solution curve goes through the point 1, 1. Let's do that in red. The solution curve goes through the point 1, 1. That would mean I'm going to try to draw a point here at 1, 1, and I'm going to follow the directional arrows like that. That solution curve would, I don't know, look about like what I attempted to draw. What if that solution curve went through, what haven't we used? Let's use purple. 2, -2. So we would start at 2, -2. I can't draw off to the right. I don't have much of a slope field there. I'd go to the right. Oh, can't go through this boundary line. Just follow that thing up here. So we can visualize what that solution curve looks like, even though we can't solve the differential equation by hand. All right, let's see if we can do this slope field a little bit quicker. So dy dx is twice the y value. We have a lot to draw here, but we're getting a little bit better. Okay. So what were we doing? Dy over dx is equal to twice y. And I know I'm trying to visualize this solution curve, but maybe I can speed things up. And I guess what I'm thinking is whenever the y value is the same, the slope I'm drawing on the slope field would be the same. So let's see. -3, 0, -2, 0, -1, 0, 0, 0, 1, 0, 2, 0, 3, 0 are all going to have the same slope. They all have the y value 0. Twice 0 is a slope of 0, a slope of 0, a slope of 0, and so on down the line. Okay. What about these ordered pairs at -3, 1, -2, 1, -1, 1, 0, 1? Those would all have a slope of 1. A slope of 2 when the y value is 2. These look right? I think I need to take my time a little bit more. Okay, let's aim right there. There. So if you're using a ruler, that's not a terrible plan. The College Board doesn't allow rulers, protractors, anything like that on the AP test. Slope of 3, so I want to connect this point, imaginary down here, that's pretty steep. So if you're not allowed to use a ruler, you need to practice without, which is why they're not sticklers on getting the exact slope. But what hopefully you can see, since in this case, the slope on the slope field is determined by the y value, the higher you look on the slope field, the steeper the slopes should get. They shouldn't look identical from row to row. Okay, let's go down. What about when the slope is, oh, the y value is -1, we get a slope of -1. A slope of -2 when the y value is -2. A slope of -3 when the y value is -3. All right. Okay. Let's pretend, like we did last time, that we were given some ordered pair. What do you want to do? Let's say 2, 2. Like we know 2, 2 is on y equals f of x, the solution curve that we're trying to visualize. So we draw a point at 2, 2, and we follow the direction of the slope field. Kind of flattens out. Ooh, and is not going to cross over the x-axis, is it? So I guess I'm looking at something like this. Maybe we can solve by hand. Let's go back to the last page and find out what we tried to solve. Separate variables, dy. Ooh, over y is equal to 2 dx. So the integral of 1 over y dy is equal to the integral of 2 dx. Let's do the easy side first. And then this is natural log of the absolute value of y, and we need some constant. So to get our equation y equals, we get the absolute value of y is e to the power 2x plus a constant, or y is equal to, really, it's plus minus, and not both, but depending on which point we know, like in this case 2, 2, well, 2, 2 is going to be the positive version. Now, we can actually solve for this c, but this is not a good point. A better time to solve for c was here, because then everything's ready to go. We have natural log of 2 is equal to 2 times 2 plus that constant. Or that constant is negative 4 plus the natural log of 2. And so now we can say y is equal to e to the 2x minus 4 plus natural log of 2. That's the solution curve we found. Or just think e to a power. Does that look like e to a power overall? It sure does.